Hey, welcome back. This is part 2 on the cylindrical grinding attachment for my surface grinder. And as you can see, I did some work off camera. I added a motor and a drivetrain, and it's practically usable in this state. And I also used it, as you saw in the teaser in the last episode. So let's talk about the details on this unit and do some minor tasks to finish it off. The motor is just one of those RC model car motors, 550 size Mabuki motors, runs on 12 volt DC and spins about 9000 RPM. I have a O-ring as a pulley, and I turned 2 pulleys. And the larger one sits on the carbide center, on the spring-loaded center, this one here. And there is a bearing in it, so while the pulley is spinning, the carbide center is stationary. It does not move with the pulley. The pulley is only spinning by itself, and there is a screw sticking out of it. And if you have a workpiece like this, just a round piece with centers in both ends, and you put this between centers, of course it's free to spin between the centers, but I added a hose clamp back here, and this engages into the drive dog, which is just a screw in the pulley here, and spins it with it. That means our part runs between 2 dead centers and is driven completely uncoupled from the centers. So we don't get any bearing noise or something like that into our workpiece. We have only sliding motion on between the centers and the center bores in the workpiece. And we can just spin the work between centers and do our grinding. A lot of people were asking how I set the taper to do, for example, Morse taper 2 grinding. That's quite simple. I use a known good taper. Let's turn this off. I use a known good taper like a Morse taper 2 drill chuck adapter, and put that between centers. Then I run an indicator along the top surface of the Morse taper, and I tilt the whole attachment in the vise until I don't get a reading or a 0 reading on top of the Morse taper, and then I'm on the right angle. Then I can take out the part, the master Morse taper, put in my workpiece, and do my grinding. And when I have done the grinding on the Morse taper, I can even flip the part around. Of course, I have to move the drive dog to the other side, and then I can grind the other side. For example, to a cylindrical end if I want to, or whatever I need to do. So one thing that's left is to polish the carbide centers. I already did a high polish on this one, but this one is still the ground finish off the single lap cutter grinder, and that's what we're going to do before we put it together finally. Okay, this is a closer view on the drive pulley. The drive dog is just a 3mm screw, and you can see, for one, the bearing. It's a shielded bearing. Those are super cheap, and if it gets damaged by the grinding dust, first of all, it doesn't matter because the bearing doesn't influence the surface finish of the grinding operations, and on the other hand, these bearings are super cheap, so that's okay. And on the other hand, you can see the surface finish on the carbide center. To compare it, I have the unpolished carbide center here, and when I bring them close up together, you can see the difference. Or not. In reality, the polished one is way smoother and has a way better surface finish than the ground one. Which makes sense, of course, because I polished them with silicon carbide stones and a diamond compound on a polishing wood, on a piece of wood. So let's go to the lathe and polish this one. Okay, we're over at the lathe and we clamp the carbide center up in a 5C collet. And I have 2 grids of silicon carbide stones here. And I have some diamond lapping compound and a piece of wood here, a mixing stick for glue. And we will use those to polish this to a high gloss. The reason for the polishing is, of course, we have sliding friction between the center and the center bore in the workpiece. And the smoother this surface is, the better the result is, and the smaller the wear on the center bore is. So there's good reason to super finish these, or to polish them. Super finishing is another process. So we start with the medium grit silicon carbide, and I use some cutting oil as lubrication. The lubrication is mainly there to get the carbide dust out of the stone. Okay, and all this dark color on my finger is carbide. Somebody asked in the comments what I mean by carbide. Carbide is, of course, in this case, tungsten carbide. And you want to get all the scratches from the previous grit out with the following. So before I jump to the fine grit silicon carbide, I want to get rid of all the grinding marks from the diamond wheel I ground this on. So I have to continue a little bit more with the medium grit silicon carbide stone. Okay, as you can see, surface finish is already pretty good. Now we continue with the fine grit silicon carbide stone. Again, using some cutting oil. You can also use petroleum or WD-40 or, in a pinch, some oil. And surface finish is already getting pretty darn good. And now for the final polish, we can use some diamond compound. Not too much, the stuff is rather expensive. Not really. I get mine from from Arc Eurotrade in the UK. They have it quite cheaply available and in a good amount of grits. This is, I think, this is 7 micron, so it's pretty rough for diamond compound. And I add some oil to the diamond compound. And then I just polish the surface. And again, all the black dirt you see there is carbide that's abraded off the workpiece. And now we get a really shiny surface. And when we're done, I have to wash my fingers because I don't want to get this diamond lapping compound all over in my shop, especially not on the slideways of my machines. That's also the reason why I covered the lathe bed with shop towel. And I will drop the collet into the ultrasonic cleaner when I'm done, because I think I get some lapping compound in there. That's not good. Okay, and now as I already have it completely apart, I can finish all the parts. I'm running them over my chamfer milling machine to give them a nice heavy chamfer, most of the parts. And the other parts get chamfered by hand with a file, and then I finish them with Scotch-Brite and a sanding sponge. Okay, I got the grinding attachment back together, but when you look at the motor, you see that the back of the motor is exposed, the connectors are open, and here the housing of the motor is also open, and you can see to the inside where the commutator is. And we don't want to get grinding dust in there, it could mess things up, so I found this piece of white there, and now I'm going to machine a cover that fits over the end of the motor to cover it, to seal it up against dust. And no, I'm not worried about overheating the motor that way, because the amperage this motor draws is very little. When I did the grinding test, it drew about, at 12 volts, it drew about 200 to 400 milliamps, and that's about 6 watt. And that's not much heat. I think that's not a problem to be dissipated over the metal housing of the motor, especially as the motor is mounted via a metal bracket to some thermal mass. Okay, as you can see, I finished the motor cover, and it went very tight on there, and I drilled the rear end to accept such a rubber grommet as a cable outlet. And there's a nice solid heavy insulated 2-wire cable, and this runs to a power supply. At the moment it's still my lab power supply, but I will see if I can get a small power supply only for this guy. And yeah, it's very tight on there, so no problems. And before we end this video, I think we will do a small grinding project. Let's see what I can find that is worth grinding. Okay, I wasn't sure what to show as an example project for the circular grinding jig, and then I found this. I made this long time ago. This is an arbor, a universal arbor to be used on a lathe. I made this to hold parts that have a hole on the inside like this. And it has a 16mm diameter here, a hard shoulder here, and a 12x1 fine thread here to hold the part. Just like this. And if you have parts with another diameter, you can quickly make such a sleeve that goes on here and increases or decreases the diameter of the arbor. Or you can make something like this. This was to hold 3 different parts with 3 different step diameters. And there's also a set of heavy brass washers to protect the part from the clamping nut when you press everything together. And you can either hold it in a chuck or in a collet, or you can hold it between centers if you have to do multiple setups back and forth. So this thing has proven quite useful, but 16mm is quite a big diameter, and for the longest time I wanted to make one for smaller diameter, like 10mm. So I took a piece of 14mm drill rod and I machined this contour here, and I hardened it to about 40 Rockwells. So it's not glass hard, but it's way tougher than in soft state. And I left on these 2 diameters here grinding allowance, 0.3mm of grinding allowance to finish grind them to diameter between centers. This one has a 8x1mm fine thread for clamping. So when I grind this will also be a very useful clamping tool for future use, and it's a good example of what can be done on the grinding jig. So let's go to a grinder and set it up. Okay, the workpiece will go between centers like this, but of course we need some way to drive it from the motor drive. And for that we use again a hose clamp, which just clamps on here and will give enough holding strength against our driving disc here to rotate the part, just like this. Okay, I set the grinding jig up on the surface grinder in the grinding vise, hooked up my power supply to the motor so I can run it at a moderate speed. And yeah, we're going to do a first test grind on the longer cylindrical diameter here. Then we're going to check if it's cylindrical, and if not, we're changing the angle of the fixture in the surface grinder. If it's cylindrical, we can continue on grinding this diameter to final diameter and flipping the part around and grind this smaller 10mm diameter in front here. So let's go. There we go. First pass. Surface finishes is rather good. Quite happy. We put a lot of heat into the part that way. That's also the reason why we need the spring-loaded center in front here. So when the part grows in length, it won't bind up between the centers. And of course it's dangerous to measure a part that's still hot from grinding, but we're checking a relative dimension from here to here and not an absolute dimension. Not yet. So I'm measuring back here. 12.3 millimeters, and in front here we get 12.19. That's 1/10 of a millimeter. That's a bit much difference. That means that the fixture is tilted up like this. This end is higher up than this end. So let's try to get this fixture down a few hundredths of a millimeter. And I'm using the dial test indicator to see what's happening. There we go. Now we can do another test grind. Okay, now we get .177 and 12.174. That's 0.03 of a millimeter difference in diameter, back to front. That's already getting pretty good. That's that's something to live with. I will give it another light tap to correct a bit more, and then I will call it good. Let's get another measurement. Okay, this part is hot to the touch. I can't leave my fingers longer than a few seconds on there, so I have to wait until it cooled down to get a proper measurement. A person cleverer than me would have set up the fog misting coolant thing, but I don't want to make a mess right now, so I have to wait and use compressed air to cool it down. Okay, I let the part cool down, and while it was hot I measured 12.01 millimeters, so plus 1/100th of a millimeter. Now as it has cooled down, I'm measuring 12.005. So while it cooled down, it shrank about 0.05 of a millimeter. And that's to consider when you're doing grinding of any way or try to work precise. Doesn't help either that I have the room heater directly behind the surface grinder, but can't change that right now. So we're taking another grinding pass. Basically, we're taking a spring pass. Okay, it was a bit more than a spring pass. I had to advance the wheel down because when the part shrank in diameter, it didn't make any more contact to the grinding wheel. So I fed down 0.003 of a millimeter, and then it was spring pass again. And when we check our diameter, I would call this 12 millimeters. On both ends. So, no.
Yes.
Oh. Okay, we ground the long 12 millimeter diameter, and now we're going to flip the part around. I already changed the hose clamp to the other end, and we're going to take it between centers again. And we're good to grind the smaller diameter on this end. I could grind it while it's in the position we ground this diameter too, but then the grinding wheel would come very close to our driving disc over here, and I don't want that to interfere with each other. Might end up with a slight crash. And I like to pick up my zero on the surface grinder by spinning the wheel by hand and moving down the grinding head. That way I can pick up a very precise zero. There we go. That was not very precise. There we go. That's our zero. Move the grinding wheel out of the way. Check for clearance. And we're good to go. Okay, we are grinding the second diameter to 10.0 millimeters or 1/100th of a millimeter undersize maximum. And this time we can just plunge down because the length we want to grind is narrower than the grinding wheel. And it's 10.1 millimeters and a few thousandths of a millimeter, but we will think those away because heat grow. You always have to keep in mind steel grows about 1/100th of a millimeter per degree temperature rise per meter of length. So a 200 millimeter long part with a temperature rise of 50 degrees will grow in length about 5/100ths of a millimeter. Keep that in mind when you do grinding. Okay, this should be pretty much to final diameter, and the part, I let it cool down for the last pass. It's not even warm to the touch. This is pretty much at room temperature. So let's take a measurement. And you saw me also move up the grinding wheel against the shoulder. The grinding wheel has a dressed side, so I touched up the register surface here of this step. And that's not too shabby. That's 10.001 millimeters. 1/1000th of a millimeter oversize. Is that 50 millionths of an inch? Something like that. I want it to be a hair undersized, so I will drop the head of the grinder 1/1000th of a millimeter, about, roughly, and take another pass. There we go. That's more like it. Okay. The very last thing I'm going to do, I will hit this this bigger diameter here very lightly with the grinding wheel, just to clean it up and make it run true to everything else. I'm not trying to hit a certain dimension with that one. We're back at my bench, or should I say at the surface plate. I cleaned the part, dropped it in the ultrasonic cleaner to get rid of any grinding dust, and now I wanted to check if this diameter runs really true to this diameter, because those two are the defining diameters of this part. And I will spin the part in a V-block and use my brand new inter-rapid dial test indicator to check the runout. A very kind viewer sent this to me. It was brand new, came in the original box, and I never had an inter-rapid indicator, but I have to say they are really nice pieces of equipment. I really like it. So kind viewer out there, I don't know if you want to have your name said online, but you know who you are, and thank you very much. So I can move the part under the indicator, look roughly for the high spot, that's the top of the diameter in other words. Then hold this whole mess together with one hand, give a bit of friction on top of the part with one finger, and then spin it in the V-block. And when you look at the needle of the dial test indicator, there is not a whole lot of movement. So I would call this a true running part. That's pretty okay. Just for fun, we can change out the indicators, move the 1/100th of a millimeter indicator out of the way, and get my 2/1000th of a millimeter indicator in. Just find a convenient spot. Get it somewhat zeroed out. Do the same thing as before, give some friction on the part so it doesn't jump on the surface roughness, and spin it. And I would say that's 1.5 division there, so roughly 3 to 4/1000ths of a millimeter total runout between this part and this part. And for the home shop, I would say that's not too shabby, and I'm quite happy with that. Also, surface finish on the part itself is, I would call that a legit surface finish. I like it. This is just like the ground finish on a tool holder, and what else could I expect? So I'm pretty sure that you're going to see the cylindrical grinding jig in other videos and other projects in the future. So thank you all for watching, and see you next time.